December 1951, a locomotive so ugly that railroads refused to buy it just outpulled 3 modern diesels combined up a mountain grade that was supposed to be impossible. What the industry mocked as Baldwin's biggest mistake was about to prove them catastrophically wrong. December 14th, 1951. Horseshoe Curve, Pennsylvania. The performance report from Pennsylvania Railroad's testing division would never fully capture what their engineers witnessed that frozen morning. A diesel locomotive that railroad executives had rejected as too unconventional was hauling 6,800 tons up a 1.8% grade that 3 competing diesels couldn't handle without helper engines. Through the snow and ice coating the Allegheny Mountains, Baldwin's RF-16 Shark Nose climbed with mechanical precision that seemed impossible given its controversial design. No streamlined nose like EMD's elegant F units, no conventional appearance that railroad purchasing departments demanded. Yet this machine delivered tractive effort that newer, prettier diesels couldn't match. If you want to see more videos about old trains that outlasted everything modern, make sure to subscribe so you never miss another video. Railroad executives had spent millions developing sleek locomotives that photographed well for company brochures. Each design emphasized aesthetic appeal over engineering fundamentals. Smooth curves, chrome accents, color schemes that pleased marketing departments. Most carried performance limitations that only light passenger service could tolerate. Baldwin was operating with an engineering philosophy the railroad industry had actively rejected. Maximum adhesion, superior traction motors, mechanical simplicity that prioritized pulling power over appearance. Quality components that transformed diesel locomotives from stylish passenger haulers into freight-moving workhorses. 900 miles from the boardrooms where locomotive purchasing decisions favored style over substance, the most decisive, mechanical revolution in railroad history was revealing itself. Not in prettier styling, not in marketing appeal, but in raw engineering capability that connected every component of Baldwin's design in ways competing manufacturers never imagined necessary. The Allegheny grades carved through Pennsylvania's mountains like a commercial death sentence for underpowered locomotives. By 1950, railroads operating these routes watched helplessly as increasing freight demands exposed their modern diesels' inadequacy. Every month brought fresh reports of stalled trains, doubled consists, requiring multiple locomotives for loads a single steam engine once handled, delays that made diesel conversion economically questionable. The performance data told the story with brutal clarity. EMD's F7 units required helper engines on grades exceeding 1.5%. Alco's FA models consumed 30% more fuel, achieving equivalent tonnage. The industry's most popular diesels succeeded in passenger service but struggled with the heavy freight that generated railroad profits. Railroad engineering departments understood they faced a choice: accept diesel locomotives' limitations and operate multiple units for loads of steam engines handled alone, or find manufacturers willing to prioritize performance over appearance. Baldwin Locomotive Works offered exactly what the industry claimed it didn't want: a diesel so focused on mechanical capability that its styling became secondary to engineering excellence. American railroads in 1950 presented a mechanical paradox that had defeated conventional diesel development. Steam locomotives delivered enormous pulling power but consumed coal and water at rates that destroyed operating economics. Early diesels offered fuel efficiency but lacked the tractive effort necessary for heavy freight operations that justified railroad infrastructure investments. The transition from steam to diesel had begun with passenger service, where locomotives pulled lighter loads at higher speeds. EMD's streamlined E and F units dominated this market through styling that railroad presidents could showcase in annual reports. Chrome grills, smooth car bodies, color schemes that made locomotives mobile advertisements for corporate brands. But freight operations demanded entirely different engineering priorities. Trains weighing 5,000 to 8,000 tons climbing mountain grades required sustained, tractive effort that passenger diesels couldn't deliver without multiple units. Operating 3 diesels to replace 1 steam locomotive eliminated any fuel savings the new technology promised. Baldwin Locomotive Works had built steam engines for 120 years, understanding rail physics that diesel newcomers ignored. Weight distribution determined adhesion. Traction, motor placement affected pulling power. Gear ratios controlled starting, tractive effort versus top speed. These fundamentals mattered more than car body styling for the freight service that generated 70% revenue. The RF-16 emerged from Baldwin's refusal to compromise engineering for aesthetics. Chief designer John Wanamaker rejected streamlining that added weight without improving performance. The shark nose car body used flat panels and angular geometry that minimized material while maximizing structural strength. Each design decision prioritized mechanical function over visual appeal. Industry reaction was immediate and dismissive. Railway Age magazine published photographs comparing the RF-16's unconventional appearance to competitors' sleek styling. Baldwin's Sharknose diesel defies every principle of modern industrial design, the editorial declared. Railroads purchasing locomotives expect machinery that represents their corporate image, not experimental styling that photographs poorly for public relations purposes. EMD salesmen showed comparison photos to purchasing agents, letting Baldwin's angular car body speak against itself. Your shareholders expect locomotives that look like the future of railroading, they'd explain while displaying their smooth F units beside Baldwin's stark functionality. The sales pitch worked because railroad executives made purchasing decisions in boardrooms, not on mountain grades. Even progressive railroads that valued performance over appearance expressed concerns about Baldwin's design philosophy. Pennsylvania Railroad's mechanical department recognized the RF-16's superior traction motors and gear ratios, but worried that unconventional styling would create maintenance complications. Non-standard components require specialized parts inventory, their technical report concluded. Long-term operating costs may offset any performance advantages. Professional engineering societies published papers questioning whether Baldwin's focus on tractive effort justified abandoning the styling standards that unified America's diesel locomotive fleet. The American Society of Mechanical Engineers warned that specialized designs created industry fragmentation that increased costs for all railroads. Ralph Johnson arrived at Baldwin's Eddystone plant in 1948 with credentials that commanded respect throughout the locomotive industry and a mandate to build diesels that actually worked in freight service. The MIT-trained engineer had studied every diesel failure on American railroads, identifying design compromises that reduced reliability and pulling power. His RF-16 would incorporate improvements that prettier locomotives sacrificed for styling. The mechanical layout eliminated unnecessary components through precise positioning of engines, generators, and traction motors. 6 Westinghouse 370D traction motors, each generating 12% more pulling force than EMD's comparable units, were positioned to maximize weight distribution across all 6 axles. Johnson's revolutionary insight focused on adhesion factors and continuous tractive effort. EMD diesels concentrated power in 4-axle configurations that limited weight per axle ratios necessary for maximum grip on steel rails. The RF-16's 6-axle design distributed 360,000 pounds across 12 driving wheels, creating adhesion coefficients that allowed full generator output to reach the rails without wheel slip. More importantly, the electrical system maintained continuous power delivery across all speed ranges. When competing diesels experience transition losses shifting between series and parallel traction motor configurations, the RF-16's generator produced constant amperage that kept pulling force consistent from 5 mile/hour to 60-65 mile/hour. The philosophy of mechanical honesty emerged from Johnson's rejection of styling trends. EMD and Alco built car bodies that pleased railroad marketing departments, then fit mechanical components into spaces remaining after designers finished with exterior appearance. Johnson designed the RF-16 from the inside out, positioning each mechanical system for optimal performance, then creating the minimum car body necessary to protect components from weather. The shark nose resulted from aerodynamic testing in Baldwin's wind tunnel, not aesthetic preferences. Air resistance at 70 mph consumed horsepower that could move tonnage. The sloped front and angular sides reduced drag by 18% compared to EMD's rounded styling, returning that wasted energy to pulling power. Component quality transformed diesel reliability through systematic elimination of failure points that plagued competing designs. Baldwin specified Westinghouse electrical equipment proven through decades of industrial service rather than experimental systems that looked advanced but broke down regularly. The main generator weighed 4,200 pounds more than EMD's unit, but produced 50% more continuous output without the overheating that limited competitor performance. Traction motor cooling used forced ventilation that kept windings within temperature limits during sustained heavy pulling. EMD's motors relied on natural airflow that worked fine in passenger service, but caused thermal failures hauling freight up long grades. Baldwin's system added mechanical complexity, but eliminated the breakdowns that stranded trains halfway up mountains. Testing protocols at Eddystone exceeded industry standards through systematic examination of every locomotive before delivery. While EMD and ALCO performed acceptance tests verifying that units met minimum specifications, Baldwin subjected each RF-16 to week-long trials that simulated mountain-grade operations. Units that couldn't maintain continuous full-power output for 6 hours without overheating were torn down and rebuilt until they achieved performance targets. The economic results vindicated Johnson's engineering philosophy during initial operations. Pennsylvania Railroad's first RF-16 hauled 6,400 tons over the Allegheny grades, consuming 3.5 gallons of diesel fuel. Performance that required 2 EMD F7 units burning 680 gallons combined to match. The ugly locomotive delivered 42% better fuel economy per ton-mile than the pretty diesels railroad executives preferred purchasing. Railroad purchasing departments in 1952 faced decisions that would determine whether engineering excellence or marketing aesthetics shaped America's diesel fleet. The RF-16 had proven its mechanical superiority on every measurable performance standard, yet orders remained scarce because the locomotive photographed poorly in company promotional materials. The aesthetic barrier became apparent during sales presentations when Baldwin representatives displayed performance data while competitors showed styling photographs. EMD's F units appeared in full-color brochures featuring streamlined locomotives pulling passenger trains through scenic landscapes. Railroad presidents could show these images to shareholders as symbols of corporate modernization. Baldwin's sales materials emphasized tractive effort curves, fuel consumption graphs, and thermal efficiency data that meant nothing to executives making purchasing decisions based on appearance rather than engineering capability. The RF-16's angular car body looked industrial and purposeful rather than sleek and modern, exactly wrong for an industry that valued style over substance. Industry publications reinforced the styling bias through editorial coverage that praised appearance while minimizing performance differences. Railway Age's 1952 diesel survey featured full-page color photographs of EMD and ALCO units alongside technical specifications. Baldwin's RF-16 received quarter-page black-and-white coverage with captions emphasizing its unconventional styling rather than superior pulling power. The passenger service bias dominated editorial perspective despite freight operations generating most railroad revenue. Writers described diesels that excelled at 80 mph passenger speeds while ignoring that most trains spent hours climbing grades at 15 mph, where tractive effort mattered more than top speed. The RF-16's design optimized for freight operations received criticism for not matching passenger locomotives' styling, rather than praise for superior performance in its intended service. Economic analysis revealed the irrationality of styling-based purchasing. Decisions when calculated over locomotive service life. An RF-16 cost $235,000. $18,000 more than EMD's F7, but delivered 2,100 horsepower to the rails compared to the F7's 1,150 effective horsepower after electrical losses. Over 20-year service life, the Baldwin's superior efficiency saved $127,000 in fuel costs while hauling 15% more annual tonnage. But railroad purchasing departments never performed these calculations because executives made decisions in corporate offices rather than on railroad property. Mechanical departments that understood the RF-16's advantages couldn't overcome management preferences for locomotives that looked modern rather than worked better. Professional resistance came from maintenance departments that opposed anything non-standard regardless of performance benefits. Railroads operating EMD fleets had developed parts, inventories, training programs, and repair procedures optimized for that manufacturer's designs. Adding Baldwin units meant stocking different components, training mechanics on unfamiliar systems, and developing new maintenance protocols. The standardization argument ignored that Baldwin's superior reliability reduced maintenance requirements that made EMD's commonality valuable. RF-16 units averaged 94% availability compared to F7 units' 87% uptime because better component quality meant fewer repairs needed. But maintenance supervisors focused on parts compatibility rather than reduced failure rates. Union resistance emerged from work rule implications of superior diesel performance. Operating agreements established crew districts based on steam locomotive capabilities requiring crew changes every 100-150 miles. The RF-16's ability to haul heavy tonnage 300-plus miles without servicing stops threatened these boundaries that protected employment levels. Railroad management facing union negotiations found it easier to purchase diesels that fit existing work rules rather than fight labor disputes over more capable locomotives. The RF-16's superior performance became a liability because it exposed inefficiencies that purchasing less capable diesels allowed railroads to ignore. Revenue Service during 1952 to 1954 generated operational data that documented the RF-16's mechanical superiority through systematic comparison with competing diesels operating identical routes under matching conditions. Pennsylvania Railroad's Pittsburgh Division provided the perfect testing ground where sustained grade separated capable locomotives from units that needed helper assistance. Horseshoe Curve represented the ultimate diesel performance test, a 1% grade climbing 1,094 feet over 9.2 miles through 3 continuous curves that limited speeds and demanded maximum tractive effort. Steam locomotives had conquered this barrier through brute force, but diesels struggled because their electrical systems overheated during prolonged full-power operation. Pennsylvania Railroad's traffic department established tonnage, ratings that specified maximum trailing loads for each locomotive type. EMD F7 units were rated for 3,200 tons westbound up the grade, requiring 2 units to handle trains that single steam engines once managed. Alco FA units rated at 2,900 tons because their traction motors overheated faster than EMD's equipment. The RF-16 received a 4,100-ton rating after testing demonstrated it could maintain continuous full power for the 47-minute climb without thermal limitations. Baldwin's superior motor cooling and generator capacity delivered performance that required 2 competing diesels working together to match. Operational economics transformed these engineering differences into measurable financial advantages. A 6,000-ton freight train required 2 EMD F7 units consuming 680 gallons of fuel for the Pittsburgh to Altoona district. The same train moved behind 2 RF-16 units using 542 gallons, a 20% fuel savings that accumulated dramatically over thousands of annual train movements. More significantly, RF-16 units could handle trains that needed 3 EMD units, reducing crew costs, maintenance expenses, and capital requirements simultaneously. A railroad could move equivalent tonnage with 3% fewer Baldwin diesels than EMD units required, recovering the higher purchase price within 3 years through reduced operating costs. Winter operations in 1903 to 54 demonstrated the RF-16's mechanical advantages under conditions that exposed competing diesels' weaknesses. Temperatures dropping below 0 degrees caused traction motor failures in EMD units that lacked adequate heating systems. Locomotives stalled mid-grade when motors froze, requiring helper engines to push disabled units and their trains to the summit. Baldwin's forced ventilation cooling system included heating elements that prevented motor freezing while maintaining optimal operating temperatures. RF-16 units operated through blizzards that sidelined competing diesels, maintaining the schedule reliability that justified diesel investment over steam power. The dramatic performance demonstration occurred March 12, 1954, when equipment failures and unexpected traffic surges left Pennsylvania Railroad short of locomotives for its heaviest westbound manifest freight. Dispatchers had 1 RF-16 available for a train normally requiring 3 EMD F7 units, 8,200 tons of high-priority merchandise that would generate substantial delay penalties if it missed connections at Chicago. The single Baldwin unit departed Pittsburgh at 2:14 a.m. with a load that exceeded its rated capacity by 4,100 tons. Engineering department observers positioned themselves at horseshoe curve, expecting the locomotive to stall before reaching the summit. Instead, the RF-16 maintained a 11 mph throughout the climb, arriving at Altoona only 12 minutes behind schedule despite pulling nearly double its rated tonnage. Generator output remained within normal operating limits throughout the test. Traction motor temperatures peaked at 287 degrees, warm but below the 310 degrees limit that would trigger automatic power reduction. The locomotive demonstrated reserve capability that competing diesels couldn't approach, regardless of how many units operated together. Baldwin Locomotive Works' financial crisis of 1956 emerged not from engineering failures but from market forces that punished quality when customers valued appearance over performance. The company that had built America's railroad industry faced bankruptcy despite producing diesels mechanically superior to every competitor. The RF-16 production line at Eddystone shut down after manufacturing just 109 units. Insufficient volume to recover development costs that exceeded $8 million. Baldwin's investment in superior traction motors, advanced electrical systems, and rigorous testing protocols created locomotives that lasted decades but sold poorly because railroad executives preferred pretty machines. EMD sold 3,600 F-unit diesels during the same period, dominating the market through styling that photographed well and marketing that emphasized appearance over engineering substance. Their locomotives consumed more fuel, required more frequent maintenance, and delivered less pulling power per unit. But railroad purchasing departments didn't measure those factors when making buying decisions. The corporate philosophy that doomed Baldwin became apparent when Westinghouse Electric acquired the company's diesel division in 1956, immediately abandoning the engineering standards that had made RF-16 units superior. Westinghouse executives saw locomotives as products to manufacture cheaply rather than machines to build for permanent service. Cost reduction replaced quality improvement as the primary objective. Baldwin's practice of testing every locomotive for a week before delivery was eliminated to reduce production time. Component specifications were downgraded to match EMD's standards rather than exceed them. The vertical integration that Baldwin had maintained, building engines, generators, and electrical equipment in-house to control quality, was dismantled in favor of purchasing from the lowest bidders. The transformation became immediately apparent in reliability statistics. RF-16 units built before the Westinghouse acquisition averaged 94% availability throughout their service lives. Units manufactured after the acquisition dropped to 81% availability as cheaper components failed more frequently. But the ultimate demonstration of abandoned excellence came when railroads began scrapping RF-16 units in the 1960s despite their superior mechanical condition. Pennsylvania Railroad retired Baldwin diesels that had logged 1.2 million miles without major overhauls while keeping EMD F7 units that required engine rebuilds every 400,000 miles. The scrapping decision reflected maintenance department preferences for standardization rather than mechanical superiority. With Baldwin out of production, parts availability became concerns that justified retiring perfectly functional locomotives rather than maintaining separate inventory for non-standard equipment. Economic analysis revealed the waste inherent in these decisions. RF-16 units retained 87% of their original pulling power after 15 years of heavy service. Their superior traction motors, built to higher standards than EMD equipment, showed minimal wear that would have supported decades of additional operation. Scrapping these locomotives while they remained mechanically sound represented destruction of valuable capital based on inventory management convenience rather than engineering obsolescence. The Strasburg Railroad in Pennsylvania operates RF-16 unit number 2006 as proof that engineering quality outlasts marketing aesthetics by generations. This 73-year-old Baldwin diesel performs revenue service in 2024. Hauling passenger trains over the same type of grades where it once embarrassed newer locomotives that were scrapped decades ago. Mechanical inspections conducted in 2019 revealed preservation outcomes that validate Johnson's original design philosophy. The 6 Westinghouse traction motors retain 91% of their original output capacity after accumulating service hours that destroyed multiple generations of replacement motors in competing diesels. Generator windings show minimal deterioration despite thermal cycling that would have required rewinding EMD equipment 3 times over equivalent service periods. The most comprehensive analysis occurred in 2022 when engineering students from Penn State measured actual performance against original 1951 specifications. The 71-year-old locomotive generated 2,087 horsepower at the rail, just 13 horsepower below factory ratings, demonstrating that Baldwin's component quality created machines that essentially don't wear out when properly maintained. Comparative data from railroad museums operating EMD-F units reveals the performance gap between engineering for excellence versus manufacturing for appearance. F7 units require complete engine overhauls every 12-15 years of active service. Traction motors need rewinding every 8 to 10 years. Electrical systems demand replacement of generators, control equipment, and wiring harnesses on similar schedules. RF-16, the 2006, operates on its original traction motors, original generator, and original electrical control systems installed in 1951. Component quality that railroad purchasing departments rejected as unnecessary expense has delivered 7 decades of reliable service, while modern diesels built for style lasted barely 20 years before scrapping. The economic consequences of industry-wide rejection of Baldwin's philosophy become apparent when calculated across America's diesel fleet. Railroads purchased 28,000 EMD road diesels between 1950 to 1970, each requiring major overhauls every 400,000 miles and complete replacement after 20 to 25 years of service. Total life cycle costs exceeded $847 billion when accounting for fuel consumption, maintenance expenses, and replacement purchases. Had the industry adopted Baldwin's engineering standards, building locomotives for 50-plus year service lives with minimal overhaul requirements, total costs would have reached approximately $340 billion for equivalent transportation capacity. The preference for pretty machines over capable equipment cost American railroads more than $500 billion while delivering inferior operational performance. Modern locomotive manufacturers have returned to engineering principles that Baldwin pioneered 7 decades ago. Current designs emphasize component quality, thermal management, and mechanical durability rather than styling aesthetics. But the contemporary industry builds these capabilities into locomotives costing $3 million each, rather than learning from Baldwin's $235,000 designs that achieve superior longevity through fundamental engineering excellence. As America's freight railroads struggle with locomotive shortages while operating diesels that require replacement after 15 to 20 years, that elderly RF-16 continues daily revenue service in Pennsylvania. Its Westinghouse traction motors will likely outlast the modern AC traction diesels that railroad executives claim represent advanced technology, providing permanent testimony that mechanical superiority dismissed for unconventional styling creates value that transcends every generation of replacement equipment built to look modern rather than work forever. Could the railroad industry have saved $500 billion if purchasing agents had valued performance data over styling photographs, when Baldwin's ugly locomotive proved engineering excellence matters more than aesthetic appeal?